Hi everyone. We extend the discussion of vectors and vector-defined objects to higher dimensions by next looking at equations of lines and planes in 4D and 5D and so on. We can express a line in a variety of ways in 2D and 3D. One format of a line that also works in higher dimensions is the point parallel form of a line, where a line is given as some point on the line, P, plus t times a direction vector v, where t is again a parameter that controls how many increments of the direction vector that we use. So we start at the point P and move some number of units in the direction v. If we take this point parallel form and split it into components, that naturally gives us parametric form. So this is only showing it in 4D, but if there was 5D, we would have 5 components, 6D, we have 6 components, and so on. So again, the parametric form translates directly in higher dimensions. And the other form that translates directly in higher dimensions is the 2-point form of a line. X of t is equal to 1 minus t times p plus t times q, where p is 1 point on the line and q is another point on the line. These three forms are defined in identical ways to how they're defined in 2D and 3D. We have to be a little bit careful. Notice that for parametric form, I didn't use X, Y, and Z. And that's because we start running out of letters very quickly. The English alphabet does not have infinite characters. It is possible to extend to other alphabet systems. We could start introducing Greek letters. We could start introducing characters from, let's say, the Mandarin alphabet. We could introduce characters from different alphabet systems. But instead of doing that, what's done is we use subscripts. So we'll say the first component is x1, the second component is x2, third component is x3, and fourth component is x4. So those are being used in place of x, y, and z for the first three. It's just much easier to go to as high a dimension as we want. Let's construct an expression of a line in these three different forms, the 2-point, the point parallel, and parametric form, given 2 points in 5 dimensions. I'll begin with the 2-point form of the line because it's the easiest one to make. And I'll just use a color code that matches the questions. So our 2-point form of a line is x of t is equal to 1 minus t times one of the points plus t times the other point. It doesn't matter which one you put where. If you put 3, 4, 7, 1, 2, if you put that as p or q, it makes no difference. I am going to label them in the order that they appear, though. 1 minus t times p, so 3, 4, 7, 1, 2, plus t times q, t times 6, 6, 8, 1, 6. Now for point parallel, I should label it as 2-point. Now point parallel. So for point parallel, we need an ingredient that's not showing. We need the direction vector. The direction vector is a vector that connects any 2 points on the line. We get that vector from the equivalent line segment q minus p or p minus q. So I'll do q minus p, 6, 6, 8, 1, 6, minus 3, 4, 7, 1, 2. So 6 minus 3, 3. 6 minus 4, 2, 8 minus 7, 1. Oh, that's not a 16. Hold on. 1, 6. 1 minus 1, 0. And 6 minus 2, 4. Okay, so that's our direction vector v. Now, x of t is equal to one of the points, either p or q. I'll use p, plus t t times the direction vector v. So that's going to be 3, 4, 7, 1, 2 plus t times 3, 2, 1, 0, 4. That's our final answer. Now the last one, parametric form, relatively straightforward to get. Parametric from point parallel. I'm not going to say x equals 3 plus 3t. I'm going to say x1 equals 3 plus 3t. And then the second component, and we'll call it y, I'm going to call it x2. x2 is equal to 4 plus 2t. And then x3 is 7 plus 1 times t. x4 is 1 plus 0 times t, so just 1. And finally x5 is 2 plus 4t. That's it. That's our parametric form of the line in 5 dimensions. For planes in higher dimensions, we give them a slightly different name. We call them hyperplanes. So a line in higher dimensions is just a line. It's not called a hyperline, but a plane in higher dimensions is called a hyperplane. The good news is that the expressions for hyperplanes are the same as expressions for planes. There's a point normal form, n dot x minus p equals 0, and there is a standard form, ax plus by plus cz plus whatever the next letter is. It shouldn't be a d, that should be some other letter. I wouldn't use d there. Let me just change that. Plus, there should be d times w, I don't know. Go back behind x. Plus something. So we start running out of letters, so it's better to write ax1 plus bx2 plus cx3 plus dx4 plus ex5 plus fx6 plus dot 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 equals something at the end, equals some constant. I'll call it h. Where that constant at the end there, that h, comes from the dot product between the normal vector and a point on the plane. Or rather, a point on the hyperplane. My apologies. So let's get a little bit of practice constructing hyperplanes from their ingredients, which is the same as constructing a plane from their ingredients. In part A, well, for both parts, we're given the point 6, 3, 5, 1, so this is a 4D hyperplane, and a normal vector with those 4 components indicated there. In part A, we're asked for the equation of the plane in point normal form. So that's the easy one for the information that we're given. Our target expression is n dot x minus p equals 0. That's the expression of the plane, of the hyperplane, and we do need the equals 0. That's part of the definition of the object. And I'm going to plug in the n. -2, 4, -3, 8 dot x minus p, which is 6, 3, 5, 1 equals 0. That's it. That's our answer. Now I'll write the equation of the plane in standard form. N gives A, B, C, D coefficients. So that's going to be -2x1 plus 4x2 minus 3x3 plus 8x4 equals h, where h is equal to n dot p. We're taking that dot product we have in the point normal form and distributing it. So n dot x minus n dot p, and then adding n dot p to both sides. So we have n dot x equals n dot p. N dot x is exactly what you see on the left hand side. N dot p is thus going to be the constant that's on the right hand side. So that's going to be -2, 4, -3, 8 dot p dot 6, 3, 5, 1. -12 plus 12 minus 15 plus 8, so we get -7. So -2x1 plus 4x2 minus 3x3 plus 8x4 equals -7. And it's worth just double checking the math, or actually double checking the copying of the numbers. -2, 4, -3, -3, 8, 8, and then 6, 3, 5, 1, 6, 3, 5, 1. Now the dot product, -12 plus 12 minus 15 plus 8. Okay, I'm happy with that. Okay, and then any type of anything else we did with higher dimensions can also be, or anything else we did with 3D can also be translated into 4D and 5D and 6D. Finding the point of intersection between a line and a hyperplane, finding the nearest distance between a point and a hyperplane, all those things translate exactly. There's absolutely no change going from 3D to 4D for any of our vector-defined objects. See you next time.